Okay, so today I'll just introduce you to the X86 assembly. It is like, understanding the assembly language is like reading the dictionary. Actually, you don't read the entire dictionary before starting speaking the first sentence in English, right? Correct? If you read the entire dictionary before you want to start uttering the first sentence, whole life will be reading only dictionary. So what we will do is that I will give you some very quick snapshot, and from there you start working, and we will give you a link to the Intel manual. It's around 1000 pages. Again, whenever you need, you can refer that manual. We will teach you how to refer that manual, and there you start, okay, and we go forward on this. Please note that what we are trying to do in the lab is really the crucial part of this course. This is what is going to you will be practically using, unless you go to a industry where you manufacture chips, or you actually start designing architecture, which probably I'll be happy even if 1% of the total population I have educated in last 16 years go and do that, I'll be happy. But many of you would land up in jobs which are going to use some of these concepts in the lab, not from the theory class. But theory has to be taught so that you appreciate the lab, okay. But unless you do this lab, this whole course is a junk, waste, crap, whatever you want to call it, okay, all synonyms of that, right. So we will concentrate much on this lab, and at the end of this we will write a small decent in the sense complex enough mini kernel of an operating system in assembly language, okay, and that is something very important and very interesting. And as you know, the X86, which is followed by Intel and the AMD, are one of the most complex instruction set computer ever in the history of computer science, ever done by mankind, okay. So it's the most toughest of the architecture and instruction set. So once you understand this, understanding any other architecture I can write and give you in blood would be the most easiest thing in your life. It will be child's play, okay. So I am going to put you into that grill so that everything else in this world becomes very easy in the area of computer organization, okay. So let us do the best on this. This lab I have been doing it for last 10 years now, and there are students who have finished within the first month. They have finished all the 4 exercises. There are cases. So if you actually spend some time understanding, all the videos are now available, the videos are shared. If you actually spend some time in understanding those videos and doing those exercises, you will be certainly in a better advantage. And if you we will give you all the 4 exercises, it will not be exactly the same, there will be some difference, and if you can complete those exercises easily, then by mid February or first week of March you can wind up this lab, and so that will be good for you, good for us, good for everyone, okay. So with all these nice things, let me start this education of X86, right. The first thing is that there is something called a memory hierarchy, right. What do you mean by a memory? What is a hierarchy? There are some entities, above that there are some more entities, above that there are some more entities, and like that. So you build. Hierarchy means layers in which one layer sits on top of the another layer, and then one on top of it and one on top of that. So one of the interesting hierarchy that we will see in this course is what we term as memory hierarchy. Memory hierarchy means what? So we have varieties of memories. The fastest of the memory is the register, which you use like a scratch pad, right, which is inside your CPU. So you just do some small computation, it is a temporary result, you just keep it in the register and then reuse it. Then there is something called cache memory, which is nothing but a replica of the main memory but smaller in size. Then there is a main memory, and then after that there is a hard disk, and all this everyone who are using every one of you who use a desktop will know about all these things, right. Now the fastest of the memory is basically called registers, and let us see how. So in the X86 we have actually 8 general purpose registers, in which 2 of them are used for certain special purpose also. So you see EAX, EBX, ECX, EDX, ESI, EDI, these are 6 general purpose registers which could be used for storing some temporary results, and then as you see down in the special purpose register you have ESP and EBP. The ESP is basically called a stack pointer and the EBP is a base pointer. The usage of these will be also we will discuss as we proceed in this lecture. Now this ESP and EBP can also be used as general purpose registers for storage purposes, right, but normally they are not used, they are used for certain specific purpose, but nothing stops you, the Intel X86 does not stop you from using ESP and EBP as general purpose registers. Now why this EAX, right. Now this is also very interesting for us to find out some history here. The first processor that came in existence was an 8-bit processor, right, which had some general purpose registers, namely we call it as AH, AL, BH, BL, CH, CL, DH, DL. There were 8 general purpose registers, each of 8 bits. Because this was an 8-bit architecture. What do you mean by a k-bit architecture? A k-bit architecture is one which can handle k bits at a time. For example, it can add 2 k-bit numbers, it can multiply 2 k-bit numbers, right. So that is what we mean by a k-bit architecture. So initially Intel had an 8-bit architecture. These are all the 8 general purpose registers, each having 8 bits, right. Then came a 16-bit architecture, but Intel did not want to keep changing lot of things, so they wanted 16-bit registers. So then they just merged these two and call it as AX, merge these two and call it as BX, merge these two and called it as CX and DX. So in the Intel machine still I can use AX, that means 16 bits, I can still say AH or AL, which means the first 8 bit and the second 8 bit of that 16 bit. So I can access AX as 16 bit in total if it is a 16 bit operand, still I can use AH and AL if they are 8 bit operands. Can you give me an example of an 8 bit operand? One 8 bit data type, characters, right, characters are still 8 bits. So if I am going to work with ASCII I can still use these smaller versions of the system. So Intel does not reserve separate AX, AX is nothing but the merging of AH and AL. So if I go and change AL, the value of AX will also change, correct. Then it introduced 4 more registers, SI, DI, SP, BP, right. This SI and DI are basically index registers, we will talk about it later. SP and BP are the stack pointer and the base pointer, again usage of that we will start. So these are all 16-bit registers. Then the 16-bit was the 8086, 8-bit was the 8085, then came 16-bit which is 8086, then came 8386 plus other machines for quite long time. This was 32-bit architecture. So what Intel did was it used this AX as the part and it extended this AX by another 16-bit and we call it as EAX. Similarly EBX, ECX, EDX, ESI, EDI, ESP, EBP. So today when we look at EAX, EAX is a 32-bit register in which the first 16 bits can be called as AX and you can access it individually. In that AX, the first 8 bit is called AL, the second 8 bit is called AH. still I can go and access AL and AH individually, right. So this is basically how the general purpose registers are used, and these registers are used for storing some intermediate computations. We will give you some examples as we proceed in this lecture. Okay. In addition to these general purpose registers, there are certain special purpose registers, and some of the special purpose registers are called segment registers. We will tell you what are segment registers later. Now there is something called code segment, data segment, extended segment, another extended FS data segment, GS another extended segment, SS is the stack segment, and E flags, which are flag registers. So there are many set of special purpose registers. We will understand the usage of these special purpose registers as we proceed in this course. We will also understand the usage of these general purpose registers as we proceed in this course. Okay. So, but what is the takeaway from this slide? The takeaway from this slide is there is something called a general purpose register, which is very fast storage, which are limited in number. We have 6 or 8 of them, and so and some 7 of special purpose registers. So these registers are inside the CPU and they can be accessed very fast. So the program, the compiler, when it compiles the program, uses these general purpose registers for quick storage and retrieval, right. It need not go to the memory. Memory is at least 2 orders of magnitude slower than the CPU. So I will not go and write everything into the memory, rather I can have a scratch pad, or this is also called scratch pad registers, so that I just keep the temporary answers and take it back. So this is about registers in X86. In contrast to what we did in the 3rd semester, where we had in the architecture we had only how many registers? 2 registers, right. Now we have 8. Now let us take this very simple code snippet. I want to convert this. So one of the important thing is that the first, as I told you, whatever we try to learn in this course will have direct implication on operating systems and direct implication on compilers, right. So whatever we learn in computer organization will be from the compiler point of view and from the operating system point of view, right. So now we will look at from the compiler point of view. So this is a C code, what you see on your left hand side, a equal to 0, while 1, a equal to a plus 1, very simple code. So how do we convert it into SX assembly? Slowly, one by one we will read the instructions, and many of these instructions, see, the out of 90% of the instructions are not used, only 10% of the instructions are extensively used. So learning even 10% is around 70, no, not even 5% or even 2% of the instructions are widely used, right. So so that means we have to learn some 20-25 instructions at the most, and we can do a fair decent conversion of your C program into assembly program. For example, let us look at this. Let us assume that A is going to be mapped onto a register EBX, right. So I say move EBX comma 0. The syntax is like this: move instruction which will move something from the right operand to the left operand. The right operand is 0, the left operand is EBX. EBX is a register. This move instruction will move 0 into EBX. Now if I say EBX is representing A in my program, then A actually gets the value 0, right. Now I increment EBX, because A is mapped down to EBX, increment EBX. INC means increment by 1. And what I do, I do jump L1. Jump is an unconditional jump, surely you should jump. Jump to L1, L1 is a label. So this will keep on incrementing. So this is essentially an infinite loop. While 1 is an infinite loop, and that while 1 gets actually mapped on to this. So this is a very simple translation of what you see on the left to a code in assembly. So what do you learn from this code? It is a very trivial code, but what we are learning is that, for example, we learn an instruction called move, in which the destination operand is the first one and the source operand is the second one. So whatever is from the second is moved to the first, right, and there are two operands to move. One is the source from which you take and put it into the destination. Now the source operand in this case is an immediate operand, it is a constant, that is why we call it as an immediate operand. Immediate means the value of what you want to move is immediately available with the instruction, correct. So that 0x0, what do you mean by 0x0? X stands for hexadecimal. So 0x essentially means whatever is going to follow 0x is going to be a hexadecimal value, and that is 0. So in this move EBX, 0x0, two addressing modes are used. One is called the immediate addressing mode, another is called the register addressing mode. In the register addressing mode I specify which register it is. In the immediate addressing mode I just give the value that I want to move. In contrast, if I had done something like move EBX, ECX, both are register addressing mode. Now the content of ECX should be moved to into EBX. The content of, now in contrast to this, what we see here is that this is the value itself is available there, 0 is available there. I am not using a register to specify that value. So that is why we call it as an immediate addressing mode. And the next one specifies the register to which I need to store, so that is called a register addressing mode. So what we have learned the move instruction, we have learned two addressing modes already here, the immediate and the register addressing mode. The next is increment EBX. So if I want to increment by 1, I need not say add EBX, 1 is equivalent to inc EBX, right. I could have written add EBX, 1 here, right. I could have written add EBX, 0x1 instead of increment EBX. So if you go into volume 2 of Intel, you will find that this will consume more bytes than this. This will consume tremendously more bytes than increment, and that is why the compiler would prefer, whenever I want to increment a register by 1 or memory location by 1, I will prefer an inc instruction rather than an add instruction. Are you able to get this? Because the add instruction will consume more bytes, while an inc instruction will consume very less number of bytes, and the add instruction will take more time to execute, inc can take very less time to execute, okay. So this is a very simple example. Now let us go to the next one. Any doubts in this? No, okay, yeah, Kavya. Okay, OX is because I wanted to teach hexadecimal here. So if you just put 0, then it becomes decimal, right, and you can also put binary if you put 0B, yeah, right. I do not know, I am not clear about try 0B and put binary, but if you just do not put anything, it is treated as decimal. If you put 0x, it is treated as hexadecimal. And I hope all of you know hexadecimal representation of data, right? Okay, okay, yeah, doubt.
We can move any constant like this, or like last time only 0 and 1 we could assign directly?
No, any constant you can put, any 32-bit constant you can put. Any 32-bit constant you can move into the EBX.
No, like directly like this.
Directly. Move EBX, whatever, what do you like, some number. Okay, you can put that, no problem. Yes. So any constant can go here. Normally you do initialization with constants, but you can initialize with arbitrary constants also, right. Can you tell me one example where initialization should be done with a arbitrary constant? So random number, right, the seed for random, suppose I am using srand, right, the seed for random should be a arbitrary value. Let us take this A equal immediately I am answering question, A equal to 0, B equal to 5, while A is less than 10, A equal to A plus 1, C equal to A by B, so much. Okay. Okay. So now, so there are a lot of things that we want to give through this code snippet. First and foremost, let us say A is assigned to EAX and B is assigned to ECX. So we just say move EAX comma 0, move ECX comma 5, that this, so A equal to 0, B equal to 5 is mapped on to move EAX comma 0 and move ECX comma 5, correct. Then I am compiling while A is less than 10, okay. So the condition needs to be checked at the beginning of the loop. So this is a loop starts, the moment I see while, I put one label here because I need to come back to that again, and I compare EAX with 0xa, 0xa means 10, decimal 10. The moment I compare EAX with A, right, then please note that we had something called a E flags register, right. So the moment I compare, the result of that comparison will be recorded in the flag register. So in the flag register you will have something called 0 flag, less than flag, greater than flag, right. So if I am comparing left with right, if left is less than right, then J less than flag will be set, less than flag will be set there. If left is equal to right, then equal to flag will be set. If left is greater than right, then the greater than flag would be set, right. So E flags may have different connotation, but let us understand it like this, right. So how do you compare two numbers? Subtract it, okay. So when will two numbers be equal by subtraction? The answer is 0, right. So when the left hand side is greater than right hand side, greater than flag would be set. When the left hand side is equal to the right hand side, 0 flag will be set because the answer is 0. So there is something called 0 flag. If an arithmetic computation gives me an answer 0, immediately that 0 flag will be set, right. And if the left hand side is greater than the right hand side, some greater than flag would be set. But for our understanding today, if the left hand side is equal to right hand side, then the 0 flag would be set. So what I do is, the moment I say compare EAX comma 0xa, at the end of this instruction one of these flags would be set. Now JZ exit, please understand what is JZ means, jump on 0. So this JZ is called a conditional jump, in contrast to the previous one which is an unconditional jump. You are not checking any condition, you keep on jumping till L1. The previous thing that you saw, JMP, is an unconditional jump, but what you see here is a conditional jump. And if what are you checking? I am checking 0. Why I am checking 0? Because if my previous arithmetic operation, did it give me a 0 result? What is the previous arithmetic operation here? Compare. It may compare gives me a 0 result, then I jump to exit. Exit is a label here. Otherwise I increment EAX because A is mapped down to EAX, and then I go back to L1. So this is a conditional jump, JZ is a conditional jump, while JMP is a unconditional jump. You got it? So till, yes, any doubts?
If JZ exit would have been below increment EAX,
Ah.
would it have checked if EAX is 0 or not?
Oh no, if I put increment EAX, if I say increment EAX, if I put JZ after increment EAX,
JZ means jump if 0. What is it going to check if it is 0 or not?
no, your previous operation, did it give you a 0 answer? That's what that's the question that we are trying to add. So if I put JZ exit after increment EAX, then this loop will never terminate, or it will terminate after 2 power 32 or 2 power 32 minus 2 power 32 iterations, correct? It will terminate after 2 power 32 iterations.
So here we come out of the while loop if EAX becomes equal to 10.
Right.
But we are checking for it should be less than 10, right? Initially suppose A was 12, we initialize it to 12, then it will go to an infinite loop.
Which one? Yeah, it will go into infinite loop.
But then as
Yeah.
per the C code it shouldn't have.
Yeah. So I should put JL. Okay. But this program will correctly execute, but this is not a faithful representation of this. Okay. Good. So could you find some enhancements to this program? I want you to start thinking. Okay. Yeah, come on. Did you understand this? When I say JZ, I as a processor will go and see the 0 flag. If the 0 flag is set to 1, I will go and do that jump, otherwise I will not do the jump, right? Now when will the 0 flag be set? If the answer of your previous arithmetic computation, if it is 0, then the 0 flag will become 1. In this case, when I compare EAX with 0XA, correct? When EAX reaches a value 10, this compare operation will make the 0 flag 1, because the way you compare is, if I want to compare A and B, I do A minus B. If that A minus B is less than 0, then I say A is less than B. If A minus B is equal to 0, then I say A equal to B. If A minus B is greater than 0, then I say A is greater than B. So this compare EAX 0XA essentially subtracts the content of EAX with 10. Are you following till now? Right. Now when EAX itself, within EAX if you have 10, 10 minus 10 essentially becomes 0, then this JZ flag, the 0 flag will be set to 1, by whom? This compare operation. Then when this JZ is executing, it will go and see whether that 0 flag is set to 1. It finds yes, it is set, then it will go and go to exit. It will not execute these two instructions. Okay? So first I start with EAX as 0, I compare EAX with 0 with 10. It is now, so if I compare 0 with 10, will the 0 flag will be set after this? Yes or no? No. So will JZ take this branch? Will it go to exit? Yes or no? No. Now I will increment EAX. EAX becomes 1. Now I do an unconditional jump back to L1. I go here again. Now I will compare 1 with 10. Will the 0 flag be set? No. Will JZ execute? No. So meaning JZ will not take the branch. So again I will come, EAX will become 2, again I go here. I compare 2 with 10, then I compare 3 with 10, 4 with 10, 5 with 10, 6, 7, 8, 9, 10. Compare 10 with 10. Will the 0 flag now be set? Yes. Now this, when I JZ, now it will take the branch, it will come here. So this loop, which comprises increment EAX, that is the only thing inside this, right? This will be executed till EAX becomes 10. The moment EAX becomes 10, then this particular instruction will not be executed. That means this is not equivalent, this will not get executed, and essentially you will come back. Correct? Are you able to follow? Okay.
If you give JZ exit and then say you give JL exit, like so it is it equivalent to checking for greater than or equal to?
JZ exit.
and then jump if more exit. Can you do that?
JL exit. Oh, you have actually JLE exit.
Yeah, I know, but like
You can give, yeah.
just giving multiple lines of.
Yeah, you can do. But what he says is JZ exit will not go and change the 0 flag or anything. It's only a jump instruction. Only arithmetic instruction will touch those flags. Okay. Yeah.
Compare flag will still be set.
Compare, no, there's nothing called compare flag. There's 0 flag, negative flag, positive flag.
Like if we do JZ exit and then JL exit, so
When you do the JZ exit, the 0 flag will not be touched. The jump instruction will not go and manipulate the flags. Okay. So what we have done here, please understand, is that I am now establishing a communication between the compare instruction and the conditional jump instruction, right. There is a communication that is happening through the 0 flag, right, between the compare instruction and the jump instruction. So there is a dependency of the JZ instruction on the compare instruction, right, rather than looking at those two others. So I am talking about this, why I am talking about dependency we will take later, but please understand, if you take the first two instructions, if I swap, nothing will happen, right. There is no dependency between that move and the next move, right, move AX and this, but there is a great dependency between this compare and JZ. Are you able to follow this, right?